Good afternoon, everyone. Welcome to a session on building smart alarms to solve safety and performance issues. I'm Sai Alamarti, Senior R&D Engineer, and along with me I have Deep Joshi, another R&D engineer here at Corva. So today I'm going to start off talking about a typical algorithm design which most of the data scientists or developers follow, and then move on to how. So there's a drawback in the typical algorithm design, and that's in how you monitor the final results. So I'm going to talk about the cons of manual monitoring, and then introduce something called smart alarms and the need for smart alarms. Then go on to how you can design these smart alarms, and give a couple of examples on how we implemented smart alarms here at Corva. So the first thing is a typical algorithm design, right? So most of the algorithms usually get some sort of input data. This can be from your drilling rig with SML data, or your completions, frac data, or wireline data. You fetch some static data, like BHA property specifications, casing specifications, or in case of a machine learning algorithm, some model that you have already trained. So those go into the calculation and the prediction part, where you either predict based on the model, or you use all the static and input data to get some calculations. Once you have your output, you store it into a database, and then you build some sort of a dashboard to visualize these results. This is pretty common in our industry and other industries. So what do you do with these dashboards, right? There's some engineer or someone who's constantly monitoring these dashboards, but it's not really scalable if that person has to monitor multiple data streams. For example, if he's monitoring 5 or 10 wells for process safety, it's not scalable to look at 10 different curves and seeing what's happening. And talking about process safety alarms, which are pretty critical, they have to be monitored 24/7. It's not that you just monitor them during the day and take a break at night. So with this manual monitoring, there's always a possibility of human error. Maybe you're looking at a curve for a wrong well. That can get pretty bad. And each shift and each person might perceive and interpret results in a different way. So that also adds to the cons of manual monitoring. So how can smart alarms help over here, right? So when I mean smart alarms, these alarms are behind the scene monitoring your final data and notifying the user or the engineer over these rigs or wells that something is going wrong. So this is easily scalable to any number of parallel data streams. These alarms are always on and monitoring 24/7. They consistently apply the same level of precision to all the wells. They don't have any bias. They also have better exception handling. So now when we have these, so that's what I already covered. So moving on to how to design smart alarms, right? I showed you the typical algorithm design which people usually take. It ends at storing the data and building dashboards. But over that, there are a few other steps you can do to make these algorithms smarter. The first step is establish some sort of norm for the calculated results. By norm, I mean some sort of expected baseline or some sort of expected range of values that it should be there, right? So those can be thresholds, some sort of trend lines, or they can be model predictions. Over here, I have a couple of examples. So here you have the black line is some data channel that's coming from the field. And then we have our upper and lower bounds, between which it's good, but if it exceeds the upper bound or falls below the lower bound, it's a bad thing. Instead of the human manually monitoring this all the time, the algorithm can automatically alert the user whenever it breaches any one of these bounds. Another example is for trend lines. So the same data curve, based on like a physics-based approach or a data-driven approach, we know that it should follow the dotted line, the trend line. But if it starts deviating from the trend line and exceeds by a certain amount, we can get another alert. So basically, the algorithm must automatically determine these norms based on the current operation that's going on the field from real-time data. In drilling, this can be automated rig state. Like if you're tripping, it could be a different threshold. If you're drilling, it could be a different threshold. And then once you have those expected values, the smart algorithm, automatically compares the calculated results with these smart thresholds and notifies the person in charge that something's going wrong. So moving on to a couple of examples of how we built a base algorithm and how we made them smarter here at Corva. The first one is an overpull detection. So the base algorithm, it uses real-time drilling data with SML coming from the rig. As you can see here, we have some of our traces. The white trace is the hook load value. And on the left, you have the block height. You can see that they are tripping. And if you can see the bit depth, they're actually tripping out of the hole. So the base algorithm captures these hook load values on the right and calculates a pickup value for each stand, like a baseline pickup value, right? What you can do in the next step is you can compare the real-time hook load with the baseline and see if you have exceeded the baseline by, say, 20 or 30%. As you can see on the top, the first stand that they pulled out, the baseline was 172 kilo foot-pound. And the next stand that they were tripping, it spiked up to 224. So that's more than 30% over the baseline. So instead of someone manually monitoring every stand that they're picking up, the alarm can automatically trigger saying, like, hey, you increased your hook load by more than 30% compared to the baseline. So it's automatically notifying the user. So the simple algorithm just captures the pickup values. The advanced algorithm builds a baseline and then compares the real-time value. This can be made even smarter by incorporating other operational concepts like breakover hook load. So every time you pick up you start picking out of slips, you see that the hook load rises up and then slowly breaks over the friction. So you can incorporate those into the algorithm to make it even smarter to avoid false positives. So that's the overpull example. We have some more process safety examples, and I'll welcome Deep to go over those.
Thanks, Sai. So another great application of smart alarms is to detect kicks. Traditionally, one of the ways kicks are detected is by monitoring the trip tank volume, identifying a starting reference point, and if the volume exceeds by more than a certain amount, to alert the rig that there might be a kick. This can be easily automated. One of the ways we've implemented it is by identifying static and dynamic thresholds that we apply to see when to start the calculation and identify when the trip tank volume goes above that limit. In the tracks here, the red curve is the trip tank volume and the blue curve on the left is the active bit volume. There are several things that can happen during an operation that might affect the reference volume that you select. One of them might be the pipe movement. As seen here, there was a pull-out. The rig was pulling the string out of the hole, as denoted by the red section right here. That affects the pit volume that you might use to reference in a kick detection algorithm. We use this as one of the exceptions that we can use to let the algorithm know, hey, don't select this as the reference, let the trip tank volume stabilize, and then use that as the reference. Another thing that might affect this referencing is transfers. During the drilling operations, there are frequently transfers from active tank to trip tank, or there are transfers from different tanks to each other. If we don't allow the alarm engine to identify this activity and not use those values as references, it might throw false positive alarms quite frequently. So we use we use this specific activity to identify trends in the active bit, trends in the trip tank volume, and with the thresholds, we let the algorithm know, hey, this is a transfer. Don't use this don't throw a false positive, or don't use this as a reference. And we allow for the trip tank volume to stabilize before it throws an alert. Another way we've been using kick detection is in flowbacks. For pump flowback, traditionally the drilling engineers would look at flowbacks for the current cycle and compare it with the valid flowbacks from previous cycles to see if there has been a gain in active or trip tank. There are several things that might affect this. The drilling engineers would use several factors to identify valid flowbacks that can be used to compare the flowbacks with. Some of these are that the flowback must be from similar bit depth. It has to be recent. It has to be of similar length and from similar flow rates. And of course, there shouldn't be any transfers or anything else that might be affecting it. All of this, doing this manually for 10 wells, you can miss a lot of alarms, or you can identify a lot of false positives. So we have been automating in our alarms. We automate this by putting all of these exceptions in the code to identify when a flowback is valid or when it's invalid, and then use only the valid flowbacks for comparison. In the figure on the right here, you can see that the fingerprinting app for one of the wells, the highlighted flowback here, you can clearly see there's something happening that's not a valid flowback. There are other flowbacks shown at the top that are either too long, too short, not recent. So the alarms algorithm that we have would identify the valid flowbacks from these based on the conditions that I described earlier, and just choose the valid flowbacks. Now we can use these and predict and identify if there's a kick happening or through gain in active or trip tanks. And so these are some of the ways we've implemented alarms in Corva. As I mentioned, manual monitoring would work well if you have one well for a smaller section, but it doesn't scale. With smart alarms, some of the ways we've implemented it and using similar methodologies, you can efficiently track drilling operations, completions operations, and drilling and completion operations both, and make sure that your operations are safe. Thank you. We can answer any questions you might have.